Hi, thank you for joining this presentation today on SPDK and infrastructure offload. My name is Jim Harris. I'm a principal software engineer at Intel, and I'm one of the core maintainers of the SPDK project. So today I'm going to primarily talk about the SPDK NVMe target and how it enables infrastructure offload. Talk a little bit about the history and the background of NVMe target, how has it evolved over time, how does it apply to infrastructure processing units or IPUs, talk a little bit about the NVMe target transport abstraction and how it enables these use cases. And then finally go into some specific extensions that we had to make to have the NVMe targets support these non-fabrics use cases. Then finally, I'm going to cover the storage management agent. This is a new feature in SPDK that we added last release, and we're continuing to evolve. I'm going to spend a little bit of time talking about how that's used for IPUs as well. Okay, so to start out, SPDK NVMe target and infrastructure offload. So just a little bit of a primer. SPDK has a fully functioning NVMe target in tree. Primarily for fabrics, it accepts NVMe commands over some network fabric, RDMA, TCP, fiber channel. It then forwards those commands to the SPDK block device, or what we call the BDEV layer. And then those commands are eventually processed by some actual storage. So this could be a local NVMe SSD. That's kind of what we're showing here. That namespace being presented to the initiator could be backed by a logical volume, so a logical partition on one of those NVMe SSDs. Or it could even be remote storage. It could be getting forwarded to another RDMA or another NVMe remote storage node, iSCSI, or even a Ceph cluster. So when we look at the history of the NVMe target, so 2016, a little more than 6 years ago, we've uploaded the first version of the NVMe-oF target to the SPDK GitHub repo. And at the time, NVMe only specified RDMA, and so that's all that the target did. But very shortly after that, just a month later, we actually upstreamed the transport abstraction. So it was becoming apparent that there were going to be new transports, TCP being the main one, and so we knew we wanted to start looking at how do we separate out common code from transport specific code. And sure enough, August 2018 was when the TCP spec, NVMe TCP spec was released by NVMe, and SPDK pushed up not only the target support but also the host driver support as well. And the following year, Broadcom took advantage of this transport abstraction and pushed up support for fiber channel in the SPDK NVMe target. And then these last couple items is what a lot of the focus will be on today, was how do we support non-fabrics use cases. So we're talking a lot about IPUs today. I'm not going to get into a lot of details on IPUs. There's probably a lot of talks at SDC this week about it. I know for sure Yadong Lee from Intel and Lev from Lightbits are doing a talk on IPUs, but then also VFI user. So for virtualization, we also want to be able to use the SPDK NVMe target to present storage to virtual machines. And so we had several cases here where we needed to extend what the NVMe target did to support some of these non-fabrics cases. And following that, Chongpong Liu pushed out the VFIO user transport code in October of 2020. So VFIO user is a initiative this has really been driven by Nutanix with support from Intel and Red Hat and Oracle to basically be able to present PCI devices to a QEMU-based virtual machine backed by a separate process. And so for SPDK, this is NVMe, presenting NVMe SSDs to a VM. Okay, so when we look at the code breakdown here, you can see that there's a lot of code that's common across all the transports. So 11 to 12,000 lines of code, and you can see that for each of the individual transports, it's much lower. And so I think this basically shows that this strategy has worked out well. It's significantly reduced the code maintenance burden, and allows us to be able to effectively use this for IPUs. So how does it apply? So this diagram here is just a simple example. We have a host that has an NVMe driver in it. It sees a NVMe PCI physical or virtual function, and so it's just going to load the NVMe driver and it is going to treat it as a PCIe device because it is a PCIe device. But on the IPU, we can have an SPDK application that's accepting commands that are coming from the host inside of an SPDK application, and we want to pass them down to a block device layer, and then we want to maybe forward them to a remote NVMe TCP target. And so the IPU is an NVMe target. It just has an IPU specific transport, and that's what we'll be talking about today. So really the goal here is share all that common code, reduce the burden. When you want to run this code base on an IPU, that you can just focus on developing some IPU specific transport code, but be able to leverage the rest of the SPDK code base on top of that. Okay, so when we look at the transport abstraction, now a lot of this has evolved over the last 6 years. Originally this was fabrics-based, so that's what I'm going to cover first. A transport implements what we call the SPDK NVMe-oF transport ops data structure, and it has a whole bunch of function pointers in it. You can look in the NVMe-oF transport.h header later if you're interested in more details, but at a high level, we have things like create and destroy. When you start the NVMe target, it doesn't automatically allocate all the resources that you need for TCP or for RDMA. You actually do a create. You do NVMe-oF transport create. Common code will do a little bit of work, and then it'll basically pass a function call. It'll call a function into the TCP or to the RDMA or whatever transport the administrator wanted to create. And same thing for destroy. Listening. So it's fairly obvious that listening for new connections looks very different for TCP or for RDMA. The administrator may want to say, I want to start to listen, and there are certain parts of that are common across all the transports. But the actual listen call, TCP, you're going to do a POSIX listen. RDMA has its own way to listen for connections. And then creating pull groups. So in the SPDK NVMe target architecture, you have what we call a pull group running on each core in the NVMe target. And the pull group is responsible for polling for new connections, or not new connections, but new requests that are coming on the queue pairs that are part of that pull group. And so when the common layer says, I need to create a pull group on each of the cores, creating the pull group looks different for TCP than for RDMA, right? You're going to have different interfaces, and TCP you're going to call POSIX listen. For RDMA, you're going to create, you're going to be using IB verbs to set up listeners. And then there's also functions to be able to add or remove queue pairs for those pull groups, and then how do you actually pull that pull group is very transport specific. And so then effectively what happens here is, in a lot of cases, the administrator is interacting with the NVMe-oF JSON RPC interface. It's calling into the common target layer. It'll do some amount of code that's common across all the transports, and then it'll effectively call into whichever transport is actually being operated on to perform some transport-specific operation. And then in reverse, the transports are the ones that are actually listening for new connections. When they get a new connection, they call the NVMe-oF target new queue pair API to tell the common layer about the new queue pair. And then similarly, when it receives a new request on one of those connections, it will call the NVMe-oF request exec function to tell the common layer, I want you to go process this NVMe-oF, this NVMe request now. Okay, so extensions for non-Fabrics use cases. So mentioned Changpeng Liu, who was doing a lot of the VFIO user work. Jacek Kalvas from Intel actually did a lot of the work here that I'm going to talk about today, as far as not just implementing what was needed here, but he actually kind of laid the groundwork for like going through what does this actually take, and found some of the cases that that we had to figure out how to address with the NVMe target framework. And so the main one is going to talk about today is how does listen and connect work for non-Fabrics use cases. So it's very obvious how this works for Fabrics, but for non-Fabrics it's a little bit different. We have to do some different handling. How do we do namespace notifications? There's some extra things we need to sometimes do for IPUs. How do we handle that? When you look at things like VFIO user or a IPU host, they are interacting with a PCIe device, so they're going to be doing register reads and writes. How does that work for Fabrics, which doesn't have PCIe bars? How does that work? And then how does a NVMe target running on an IPU report features that are different than what you would expect from a Fabrics target? So first, listen and connect. So we'll start with just a simple example with TCP. Listen means we are going to start listening for TCP connections on a given address and port. So the administrator says, I want you to listen on this IP address, on this TCP port. We use POSIX listen call to start listening for to start listening for that. And then we call accept. So accept, at some point we call accept. It may return a new TCP connection. That tells the transport to start processing data, start processing the data stream and parsing that into NVMe capsules that can then be passed down to the common NVMe target layer. And then connect. So we talk about the TCP connection. That's just at a TCP layer. Now we have the initiator and the target that can send bytes between each other. But at a higher layer, you have the NVMe Fabrics connect command, which basically is a NVMe capsule that says, I want to associate this connection with a certain NVMe subsystem on the target. And so this NVMe Fabrics command, this is part of the spec. Every transport's required to send this to do that association. But IPUs and like virtual machines with VFIO user, it's not a Fabrics transport. It's PCIe, and so you're not going to get an explicit connect command from the host. So how do we handle that? So if we go back and we kind of look at how the listen operation is configured, the administrator basically says, I want to add a listener for a specific NVMe-oF subsystem. So we've already created a subsystem. Now we want to enable listening for connections, and then these connections are allowed to connect to that subsystem. So the first thing we have to do is just to set up the listener. So there could be a lot of cases where you want to use the same IP address and port for multiple subsystems. So the first thing we just do is we say, are we already listening for connections on this address? If we are, that's great. If not, well, now we create a new listener. But the difference here is that at this point now, we also need to tell the IPU that, look, when you get a connection for this address, so IPUs are going to have their own way to specify what a listen address is. It's not going to be an IP address and port. It's going to be something else that's defined by the IPU, which is outside the scope of this talk. But once that listener is there, the IPU is going to get a connection. And the IPU has to know, because it's not going to get a connect command from the host, it has to know which subsystem is this going to be associated with. And so what we actually do is we have a new call called the listen associate, which tells the IPU, when you get a connection, I want you to connect to this subsystem using a fake connect command. And so this is how we handle this in SPDK. The IPU then at some point later on, the host comes up, it does something, it initializes the NVMe device, it comes out of reset, and the IPU transport sends a fake connect command to the common layer saying, okay, here's a connection and I'm going to connect to this specific subsystem. And so this allows us to use all the same connect handling for associating queue pairs with subsystems the same way for non-Fabrics use cases as we do for the standard Fabrics ones. Next, namespace notifications. So for Fabrics, everything is handled in band. The host can enumerate namespaces using identify commands, identifying namespaces. They can submit asynchronous event requests that then get completed later if the controller has namespaces added or removed, or if the namespaces change. So all of this is handled in band. But for IPUs, they may have they may require some special handling when namespaces are added or removed. Maybe there's something in the RTL that has to be notified to be able to accept commands for different namespace IDs. There's any number of things that could happen here. And so before we were covering these non-Fabrics cases, we didn't notify the transport about them because the transport didn't need to know. And so now we've added additional ops for the transports to optionally implement so that they're notified whenever a namespace is added or removed. And so then this allows the IPU to do whatever special handling it needs to do for those cases. Next, register reads and writes. So in NVMe, we use the term property instead of register, but they're effectively the same. In Fabrics, the host will send property get or property set commands to either read from or write to registers like controller configuration, controller status, capabilities, version, etc. So it'll send a bunch of these commands during initialization, and then the target will process them. But again, for non-Fabrics, this is all effectively PCIe based, so you're not going to get Fabrics commands. It's going to read and write registers to a PCIe bar. And so what we do here is that when the IPU transport or the VFIO user transport, when it detects a register right from the host, it basically translates that into a property get or set command and sends that down to the common layer instead. And so this allows us to simulate PCIe register accesses in a way that's common. It allows us to have common handling across Fabrics and non-Fabrics. And then finally, there's other nuances of non-Fabrics controllers. So for example, in Fabrics, you always report that it supports SGLs. So if you're not familiar with NVMe, NVMe defines something called PRPs, physical region pages, and it's a very simplified way of for the host to describe host memory for an NVMe command. And so a controller can report whether or not it supports SGLs. Fabrics controllers do not support PRP. PRP is not part of the Fabrics spec, so Fabrics controllers always report that they support SGLs. But there are IPUs that may not support SGL. They may only support PRP, and we need to allow a way for the IPU transport to be able to express that. And so what we do is we've added a new, we call C data for controller data, or this is the identify controller data. It allows the transport to initialize that data to override certain fields in that data structure. So for example, if there's an IPU transport that doesn't support SGLs, it only supports PRPs, it can clear that bit. And then what that enables is, later on, once identify controller commands are sent down from the host, we can do all the same processing for those commands, whether it's coming from a Fabrics queue pair or whether it's coming from a VFIO user or an IPU queue pair. Okay, that was a lot. If you want to get more information, I mentioned Yadong and Lev's talk. There's also a talk given by Tomek Svatsky and Jarek Kogut from Intel, where they're talking also about SPDK and IPUs. Check out their online talk as well. Next, I want to cover the storage management agent. So when we talk about SPDK and IPUs, how do we orchestrate them, right? So now you have all these IPUs and these different hosts. How do you orchestrate, I want to connect, I want this VM or this host to be able to connect to this remote storage through this IPU. And so when we look at SPDK applications, the JSON RPC interface, which we primarily use for configuration, is intentionally very low level. So, we made this decision. We wanted to make it where you can build higher order constructs on top of it. And inside of SPDK, it just does kind of the bare minimum. So it gives you all the pieces and you can build code on top of it to do what you need. But what this means is that when you want to connect an IPU host to like that backend NVMe TCP storage, there's a whole bunch of steps that you have to go through, a whole bunch of different JSON RPCs, and some of those RPCs may fail, and that means that then you need to make sure you know how to walk back and undo what you had already done. And so this can be a little bit onerous if you're developing some kind of orchestration agent like a Kubernetes CSI node driver. So for example, the basic steps for what I was just talking about is first you do bdev NVMe attach controller. So you tell the IPU, go attach to this remote NVMe TCP subsystem. And then you tell the NVMe-oF target layer, I want you to create a subsystem. This is a subsystem that's going to be presented to the IPU host. And then we discovered some namespace on that NVMe TCP subsystem, and we're going to attach that or add it to the NVMe subsystem. And then we have to add a listener, right? We need to tell the IPU, you may have multiple virtual functions or physical functions on this IPU. This PF or VF is associated with this subsystem. And so we need to add that listener so that the IPU knows how to connect the two. And then we may even have IPU-specific RPC parameters. So I think IPUs can be arbitrarily complex. They may have different parameters and things that need to be passed, and that can be different from vendor to vendor, or even different IPUs from the same vendor. And so the question here was really, how do we make it easier to write something like a Kubernetes CSI node driver? And so that's where SMA, the storage management agent SMA, comes in. So Konrad Steiber from Intel has been really driving a lot of the design and development on this with input from others at Intel and Lightbits and the community. And effectively what it is, it's a gRPC-based application that's sort of like a sidecar to the SPDK application running on the IPU. And its purpose is to attach existing storage to the host. So provisioning is out of scope here. So the idea here is that you may provision the storage on the remote NVMe TCP target. That's going to be done separately. SMA is responsible for how do we connect to it and then present that up to the host. And so in contrast to the SPDK JSON RPC interface, SMA has a very basic operation set. Create device, delete device, attach volume, detach volume. Create device also has an optional, you can pass a volume that you want to attach to it when it's created. So in a lot of use cases, if you are just presenting a single volume to the host, you've got one call to SMA, it's just create device. You may pass a bunch of parameters to it, but SMA is going to take care of making sure that it does all the JSON RPC calls. If one of them fails, it rolls things back. It handles all that complexity so that the Kubernetes CSI node driver has a much simpler interface to be able to talk to. And so inside of SMA, we have the device manager class, and IPUs are effectively responsible for implementing that to whatever specific is for their IPU. And so, then the idea here is that the Kubernetes CSI node driver is just talking to SMA if it's running on multiple different types of IPUs from different vendors, different IPUs from the same vendor. The Kubernetes CSI node driver itself doesn't need to change. It's still just talking to SMA. The responsibility is on starting SMA up, doing any startup configuration, and making sure that you have that device manager implemented for whatever is specific for that IPU. So the current status, I'm going to call Rev 0.1. This is still very much work in progress. This is very new space. So development is still very much ongoing here. We have device managers for VFIO user, which sort of emulates an IPU from the perspective of you have an SPDK process running on a host that's presenting storage to a VM. So NVMe VFIO users use there. We have vhost block, which is effectively the same thing, but for VirtIO, right? You're presenting a VirtIO block controller from an SPDK process to a VM. The vhost block device manager allows you to use SMA to be able to orchestrate that. And then we have one for NVMe-oF TCP as well. So you can use this with a TCP target. That's maybe not the primary use case, but it's very useful for testing as we go through and we, prove out the device manager interface and how this is all going to work. Currently on the back end, it only supports connecting to NVMe TCP volumes on the back end. This will likely be extended over time, but that's where the support is there today. And then in progress, there's patches out right now that are under review for specifying data encryption keys. So for being able to encrypt data as it's coming from the host through the IPU, potentially out to remote storage. And then also quality of service parameters. So how do you specify maximum IOPS if you have one IPU that's serving storage to multiple VMs on that host? So that's it for today. Thank you for listening. Hope that you found this information helpful. If you have any other questions, you can find me or others in the SPDK community out on our Slack channel. Go out to spdk.io/community for details on how to connect there. Thank you.